Let me begin by asking you to do something deceptively simple. Look at a clock. Watch the second hand move. Each tick feels identical to the last, steady, reliable, universal. You assume, as nearly every human being who has ever lived has assumed, that this moment, this now you are experiencing, is shared by every person on Earth, every astronaut in orbit, every atom drifting in the void between galaxies. You assume that time is a river, and that all of us float upon it together, carried at the same pace toward the same future. You are wrong. Not slightly wrong. Not wrong in some trivial, academic sense that only matters in a particle accelerator or a theorist's notebook. You are fundamentally, profoundly, beautifully wrong. And the story of how we discovered this how, a 26-year-old patent clerk in Bern, Switzerland, dismantled humanity's most basic intuition about the nature of reality, is one of the most extraordinary chapters in the history of human thought. It is a story about light, about motion, about the strange and unsettling truth that the universe does not work the way it appears to work. It is, in the deepest sense, a story about what time actually is. In the year 1905, Albert Einstein published 4 papers that would reshape the landscape of physics. One of them explained the photoelectric effect and would eventually earn him the Nobel Prize. Another provided definitive evidence for the existence of atoms, but it was the third paper, titled On the Electrodynamics of Moving Bodies, that detonated like a quiet bomb at the foundations of everything we thought we knew. In that paper, Einstein laid out what we now call the special theory of relativity, and in doing so, he severed time from its throne. Time was no longer absolute. Time was no longer universal. Time was no longer universal. Time, Einstein showed, is personal. It depends on how you move, and the key to understanding why the thread that, once pulled, unravels the entire fabric of classical intuition is light. To understand what Einstein did, we need to start with 2 ideas. Just 2. They sound almost innocent when you first hear them, almost obvious. But taken together, followed rigorously to their logical conclusions, they produce a revolution. The first idea is this: the laws of physics are the same for everyone moving at a constant speed. If you are on a perfectly smooth train gliding at 100 kilometers per hour and you toss a ball into the air, it behaves exactly as it would if you were standing still on the platform. There is no experiment you can perform inside that train, no measurement of motion, no observation of any physical law that will tell you whether you are moving or stationary. Motion, in other words, is relative. This was not new with Einstein. Galileo had said as much centuries before. It is the second idea that changes everything. The second postulate is this: the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source of that light. Let that sink in for a moment, because it defies every instinct you have. Imagine you are standing on a road and a car drives past you at 60 kilometers per hour. The driver throws a ball forward at 20 kilometers per hour. To you, standing on the road, the ball appears to be moving at 80-60 from the car, plus 20 from the throw. This is how velocities add in everyday life. It is intuitive, it is obvious, and it is not how light behaves. If that driver turns on the headlights instead, the light does not move at the speed of light plus 60, it moves at exactly the speed of light. If you chase after that beam in a spaceship at 90% the speed of light, you will still measure the beam moving away from you at the full speed of light, not 10% of it, all of it. No matter how fast you go, no matter how cleverly you try to catch up, light always recedes from you at precisely 299,797,258 meters per second. This is not a quirk. This is not an approximation. This is a law of the universe as fundamental as any we have ever discovered, and it was confirmed long before Einstein built his theory upon it. In 1887, Albert Michelson and Edward Morley conducted one of the most famous experiments in the history of science. They attempted to measure the difference in the speed of light as the Earth moved through space in different directions, reasoning that light traveling with the Earth's motion should appear faster, and light traveling against it should appear slower, much as sound travels differently with and against the wind. They found no difference at all, none. The speed of light was stubbornly, mysteriously constant. The experiment was considered a failure at the time. It was, in fact, one of the most successful measurements ever made. It told us something astonishing about the universe, and it took Einstein to understand what that something was. Here's the problem. If the speed of light is the same for everyone, then something else must give. Something must be flexible, something must adjust, to accommodate this cosmic speed limit that refuses to change regardless of who is watching. And what gives, what bends, what stretches and compresses to preserve the constancy of light is time itself. Let me show you why. Imagine a simple device, a clock made of light. Two mirrors, one above the other, with a single photon bouncing back and forth between them. Each time the photon completes a round trip up to the top mirror, back down to the bottom, that counts as one tick. This is a perfectly good clock. Now imagine this light clock is sitting on a spaceship, and the spaceship is moving to the right, at an enormous speed, let us say, half the speed of light. You are watching from outside, standing still. What do you see? From your perspective, the spaceship is moving, and so the light clock is moving with it. The photon is still bouncing between the two mirrors, but now, because the whole apparatus is sliding to the right, the photon does not travel straight up and down, it travels diagonally, up and to the right, then down and to the right. A zigzag path. And here is the critical point. A diagonal path is longer than a vertical one. The photon has to cover more distance on each bounce, but the speed of light is the same. It cannot go faster just because it has farther to travel. So what happens? The ticks take longer. The clock runs slower. Time on that moving spaceship, as measured by you standing still, is genuinely, physically passing more slowly. This is not an illusion. This is not a trick of perception. The clock is not malfunctioning. Every process on that ship, every heartbeat of its passengers, every chemical reaction, every electrical signal in every neuron of every brain is happening more slowly. Time itself has slowed down. And here's the part that bends the mind. For the passengers on the ship, nothing feels different. Their light clock ticks at what seems to them a perfectly normal rate. Their hearts beat at a normal pace. They experience no slowing, no stretching, no distortion of any kind. From their perspective, they are standing still, and you are the one who is moving. And from their perspective, it is your clock that is running slow. Both of you are right. Neither of you is wrong. There is no privileged frame of reference, no God's eye view from which one of you can be declared the real stationary observer. This is the relativity of time, and it is absolute. The mathematics that describe this effect are captured in what we call the Lorentz factor, but we do not need the equations to grasp the essence. At everyday speeds, driving a car, flying in an airplane, the effect is vanishingly small, so tiny that it was invisible for the entirety of human history before the 20th century. A passenger on a commercial airplane experiences time slightly more slowly than a person on the ground, but the difference amounts to a few nanoseconds over the course of a flight. It is real, but it is negligible. However, as you approach the speed of light, the effect grows dramatically. At 90% of the speed of light, time on the moving ship passes at roughly 44% the rate of time for the stationary observer. At 99%, it drops to about 14%. At 99.99%, time virtually grinds to a halt. And at the speed of light itself, if you could somehow reach it, which for anything with mass you cannot, time would stop entirely. A photon, from its own perspective, if we can even meaningfully speak of such a thing, does not experience time at all. It is emitted from a star and absorbed by your retina, and for the photon, those two events are the same event. The billions of years and billions of light years between them collapse to zero. Light does not travel through time. Light exists outside of it. Now let us push further into the strangeness, because time dilation is not the only consequence of Einstein's postulates. There is another effect, equally disorienting, called the relativity of simultaneity. Imagine two events, say two flashes of light that occur at different locations. A flash at one end of a long train platform and a flash at the other end, happening at exactly the same moment. A person standing in the middle of the platform sees both flashes at the same time and concludes they were simultaneous. But a passenger on a train speeding through the station, also positioned midway between the two flash points at the moment they occur, sees something different. Because the train is moving toward one flash and away from the other, the light from the approaching flash reaches the passenger first. The passenger concludes, correctly within their frame of reference, that the flashes were not simultaneous, that one happened before the other. And here is the disquieting truth. There is no objective fact of the matter about which events are simultaneous and which are not if those events are separated in space. Simultaneity is not a feature of the universe. It is a feature of your motion through it. Two events that are simultaneous for you may occur in a different order for someone else. The past, the present, and the future are not absolute categories. They depend on where you are and how fast you are going. If this sounds like a thought experiment too exotic to have practical consequences, consider this. These effects are not theoretical curiosities. They are engineering requirements. The global positioning system, which billions of people rely on every day to navigate their cars, find restaurants, and coordinate logistics across the planet, depends on the precise correction of relativistic time dilation. GPS satellites orbit the Earth at roughly 14,000 kilometers per hour. That is fast by human standards, but it is a crawl compared to light. Still, even at that modest speed, special relativity causes the satellite clocks to tick slightly slower than clocks on the ground by about 7 microseconds per day. There is also an opposing effect from general relativity, Einstein's later, even more profound theory of gravity, which causes the clocks to tick faster because they are higher in Earth's gravitational field, by about 45 microseconds per day. The net effect is that satellite clocks gain roughly 38 microseconds per day relative to ground clocks. If this were not corrected, GPS positions would drift by approximately 10 kilometers per day. Within a week, your navigation system would be useless. Every time you use GPS, you are relying on Einstein being right, and he is. There's another confirmation, one that comes from the subatomic world and is arguably even more elegant. High in the Earth's atmosphere, cosmic rays, high-energy particles from deep space, collide with air molecules and produce showers of subatomic particles, among them muons. Muons are unstable. They decay with a half-life of about 1.5 microseconds. Given their speed and the altitude at which they are created, a simple calculation shows that most of them should decay long before reaching the Earth's surface. They should not survive the journey, and yet they do. Detectors at sea level register far more muons than should be possible if time passed for them at the same rate it passes for us. The explanation is time dilation. The muons are traveling at speeds very close to the speed of light. From our perspective on the ground, their internal clocks are running slow. Their decay process is stretched out in time, so they live long enough to reach the surface. From the muon's perspective, if we could adopt it, the explanation is different, but equally valid. The distance between the upper atmosphere and the ground is contracted, shortened by the Lorentz contraction, so the journey is shorter than we think it is, and they have enough time to complete it. Both descriptions are correct. Both are real. The universe accommodates both because space and time are not independent stages on which physics plays out. They are part of the play itself. And this brings us to perhaps the most profound insight of all the insight that transforms special relativity from a collection of strange effects into a coherent vision of reality. In 1908, 3 years after Einstein published his paper, the mathematician Hermann Minkowski gave a lecture that began with a declaration that has echoed through physics ever since. Henceforth, he said, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski had realized was that Einstein's theory was not merely saying that time behaves oddly at high speeds. It was saying something far deeper, that space and time are not separate things. They are two aspects of a single four-dimensional entity, spacetime. Just as the length and width of a shadow change depending on the angle of the light, but the object casting the shadow remains the same, so too do the space and time measurements of an event change depending on the observer's motion, but the underlying space-time interval remains invariant. When you move through space faster, you move through time slower, and vice versa. There is a trade-off, a cosmic budget, and the currency of that budget, the quantity that remains constant and universal and unchanging no matter who is doing the measuring, is the speed of light. Think of it this way. Right now, as you sit listening to this, you are moving through space-time at a fixed rate. If you are sitting still in space not moving relative to the Earth, then all of your motion is directed through time. You are hurtling into the future at the maximum possible rate. But the moment you begin to move through space, some of your motion through time is redirected. You move through time a little more slowly. The faster you move through space, the slower you move through time, until, at the speed of light, all of your motion is through space and none is through time. This is why light does not experience time. This is why nothing with mass can reach the speed of light. It would require redirecting all of your temporal motion into spatial motion, and for a massive object, this would require infinite energy. The speed of light is not just a speed limit. It is the exchange rate between space and time. It is the fundamental constant that weaves the geometry of reality. In Minkowski's spacetime, events do not simply happen at a place and a time. They happen at a point in the four-dimensional manifold, and different observers slice that manifold differently, like cutting a loaf of bread at different angles. Each slice is a different now, a different set of events that the observer considers simultaneous. Your now and my now are different cuts through the same block of space-time, and if we are moving relative to each other, our slices are tilted. What is in my future may already be in your past, not because information has traveled backward, but because the geometry of space-time allows different observers to partition events differently. The block universe, as philosophers call it, simply exists, past, present, and future laid out together like pages in a book that has already been written. Whether this means the future is determined, whether free will survives the geometry of Minkowski's spacetime, whether the flow of time is an illusion produced by consciousness navigating a static four-dimensional structure, these are questions that physics alone cannot answer. But it is physics that forces us to ask them, and so we arrive at the philosophical heart of the matter. For thousands of years, time was considered absolute. Newton wrote that absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. It was a backdrop, a stage, a ticking metronome against which the drama of the universe unfolded. Einstein destroyed this picture. Time does not flow equably. Time does not exist independently of the things moving through it. Time is entangled with space, warped by velocity, stretched by gravity, personal to every observer. There is no universal now. There is no master clock ticking away at the center of the universe, keeping the official time. Each of us carries our own time with us, and it runs at a rate determined by our path through space-time. The astronaut who spends a year orbiting the Earth at high speed returns to find that she has aged less than her twin who stayed on the ground. This is not metaphor. This is measured fact. The difference may be small with current technology, but it is real, and it grows without limit as speeds approach that of light. Time is not what we thought it was. What does this mean for us, as human beings trying to make sense of our place in the cosmos? It means, at a minimum, that the universe is stranger and more wonderful than our everyday experience suggests. We evolved to navigate a world of medium-sized objects moving at medium speeds, and our intuitions are calibrated to that world. We feel that time flows, that the present is special, that simultaneity is obvious, that a second is a second is a second. None of this is wrong in the practical sense for the speeds and scales of everyday life. Newtonian physics works beautifully, and our intuitions serve us well. But at the edges, at the extremes, where speeds approach light and distances span galaxies, the universe reveals a deeper architecture that our intuitions cannot reach. And it is precisely there, at those edges, that we find the truest description of reality we have ever achieved. There is something humbling in this, but there is also something exhilarating. We are a species that evolved on a small rocky planet, orbiting an ordinary star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. And yet, from this tiny perch, using nothing but our minds and our instruments, we have uncovered the geometry of space-time itself. We have learned that light is the thread that sews space to time, that motion is the needle, and that the fabric they produce is the universe we inhabit. We have learned that time is not a river carrying us forward, but a dimension we move through, and that our rate of passage through it depends on how we move through the others. We have learned that the universe does not owe us simplicity, and yet, beneath its bewildering surface, there is an elegance so profound that it takes the breath away. Einstein once wrote that the most incomprehensible thing about the universe is that it is comprehensible. Perhaps that is the deepest lesson of special relativity, not merely that time dilates, or that simultaneity is relative, or that space-time is a four-dimensional manifold, but that a mind made of atoms can look at the universe made of those same atoms and understand something true about its structure. That the language of mathematics, spoken by beings who learn to count on their fingers, can describe the curvature of space-time and the behavior of light across billions of years. That we can know these things at all. So the next time you glance at a clock, let yourself feel, if only for a moment, the strangeness beneath the ordinary. That steady tick is not a universal heartbeat. It is your heartbeat, marking your particular path through the four-dimensional fabric of existence. Someone moving differently would hear a different rhythm. A photon would hear none at all. And the fact that you can understand this, that you can hold in your mind the knowledge that time is personal, that space and time are one, that light is the thread that binds them, places you among the most remarkable arrangements of matter the universe has yet produced. You are space-time, contemplating itself, and that, perhaps, is the most astonishing thing of all.